and give us the same level of productivity improvement that we had over the period of years. And this is where you will come up with lots of machine learning models, which will discover correlation. Our challenge now is how do you put causation on these machine learning models where you can capture human expertise, which people have acquired over years. How can we complement with that expertise so that you start making intelligent decisions? And that is really a framework of digital twinning process. So the novelty that what we are working on is how do we represent this product-specific process knowledge in a graph database and use that for your decision-making process. So when I was a Royal Academy of Engineering fellow, which was now almost 5 years ago, and we did work with International Foundry in India as a part of that fellowship. What our challenge was that if I get my outputs, which is on the right-hand side, and there's a deviation from those outputs because your rejection rates have gone up, customer complaints have increased as compared to your traditional baseline, then you want to then penalize that response and transfer it back onto your process. So this is for investment costing process. So you could have rejections in your wax process or shell making process or casting process or the inspection process. So you need to be able to figure out where can I change my knobs to minimize my occurrence of defects and make sure that it doesn't happen again. That's really root cause analysis. So you capture a lot of data, and that ability is in people's head. And then how can we use that ability in a meaningful way? That's the research work we've been trying to do. So normally in your manufacturing process, you have SPC charts where you will monitor your key process variables with a target value, and they will have some tolerance limits. Then you have control plans. Everybody needs to monitor FMEA, and we'll talk about FMEAs and how they are progressing with new VDA AIAG guidelines and how we can go beyond those guidelines, which will then help us to capture AI. So in that process, you then need to start looking at your optimal process specifications, your continuous improvement actions, and then you capture your data. And the whole objective is how do I integrate all of this together? And in that process, we publish, again, this is long back on your product-specific process knowledge, which is a list of optimal factors and ranges which meets your desired business goals. And if there's a deviation of desired business goals, we penalize deviation across your factor data to come up with, to help you figure out, root causes. So recently we developed a very complex model, which is published 2 years ago, on developing from small data sets, which is what foundry industry normally has, on predicting your root causes. And this is currently under review, where we can, it is based on random forest model, where you can augment your data to make your predictions more realistic. Again, these are machine learning algorithms. The key challenge, which we are currently working on, is how do you use generative AI to replicate your root cause analysis? So you start with 5 whys, and these 5 whys, instead of asking to a person, imagine you are asking it to a computer. And imagine that computer is responding back to you like an intelligent person. And that is where we see the future is going to. And that's why the generative AI has really given us step change thinking in the way we approach and use the knowledge. And the way it does, we've done this coding using vector embeddings. And you see this paragraph, which is like a English paragraph, which describes particular function. And AI will then convert that into a vector, and you get these magic numbers. And then you do cosine similarity of those numbers, and it just happens to be the similarity of intent. And the key thing that we found here was the difference between the milled slot and drill hole. It could be spurious, but it caught our attention because for the root cause analysis, experts will know that the mill slot is really a blind hole in terms of the knowledge that you're going to use for root cause analysis. So the point that I'm trying to make is this, it is not a hype the way ChatGPT has improved. Of course, there are other LLM models which will sit in your intranet, and your knowledge does not become publicly available. But that's the research direction we are going on. And what we have done using these new guidelines of FMEA and VDA, AIAG VDA guidelines, we use those guidelines and we put this knowledge in the form of graph database. And that then allows us smooth integration with large language models to help work with industries to help them solve root cause analysis. There's a lot of work required, but at the moment, our experience is Foundry industry is doing this work halfway through. They're spending energy to maintain all this data, but they're not really benefiting from the revolution. And that's the gap we want to address, and we are working with industry. So that's really work in progress of how this relationship very quickly zoom out into a very large number of nodes. So what we are looking at is the framework that we will launch in next couple of months. And we are actually working with a multinational foundry in South India. I mean, I just had a meeting with them an hour ago based on our weekly meetings. So what I would like to take the opportunity is, the work that NIAMT doing is excellent in trying to provide a platform of linking industry and academia together. And what I'm quite interested in is to form this consortium with our relationship with South African industry, UK, and India, and develop working together on exchange of ideas, etc. So if I was in person, I could have had chat with you, in person, but I would like you to sort of, give your thoughts and explain your apprehension. I mean, 20 minutes is a very short time to communicate. I hope I've not rushed it, but I open the topic to the floor to ask questions on whatever I've presented, and also how we can interact with each other by working with, for example, NIAMT, so that everybody's time is spent efficiently. Yeah, I mean, I've tried to sort of, done it in 15 minutes. Are there any questions?
So, any question from here? Any questions?
So, how you will identify the defect, and if defect is identified, then how software will be read to identify the root cause and corrective action and PFME?
Good question. So identification of defect is, as you say here, is in detection control.
Yes.
So you can separately create a pipeline to use visual inspection or other techniques to automate that process. But we assume that the defect is identified by either expert or through inspection process. And then we are using that knowledge to find root cause analysis. So we want to replicate what happens in your daily quality control meetings when your group of experts come together in the morning and then they make decisions on the corrective actions, what happened, what can I change? So we want to replicate that thought process and explore if computer can help improve productivity so that the expert can manage whatever the expert time is happening.
Domain knowledge is inevitable. Rajesh, I'm Sham here.
Oh, hello, Mr. Arjunakar. Yes. Nice to.
I will just add to what you have said in a simple language. The domain knowledge is inevitable. So with your domain knowledge, you identify the defect. So you know what is defect. And then subsequently, as he has said, all that path could be followed to take care for the remedial action. And remedial action, when we are interacting, all the things that you should not think of the sixth sense. You should not go with the bias. You should understand your process. You should know your process parameters, and you should have that analytical mind and analytical algorithm ready with you to help you out. So that will reduce the burden, as he has said, of an expert who is going to give the remedial action. That is the crux of the matter.
Thanks, sir, for explanation. This means brainstorming will be done by the software, not by the team.
Say it again. I missed it.
Yes. Okay.
Can you say the question again, please?
Just I'm telling, as I understand, the brainstorming to identify that things will be done by the software. Brainstorming process.
Yes, but the best way to visualize it, it's not going to take over decision-making process. It's going to assist quick decisions by expert.
Yeah.
So we want to make the decision-making process very, what you call, time efficient.
Got it.
And the challenge there is how do you capture, as Mr. Arjunakar has just said, somebody's experience, so the person has acquired in, say, 20 years. How can we capture that experience and reuse it so that fresh graduate engineer can make those decisions on behalf of experts? And what we want to test, that 99% of the time, those decisions should be correct. So that is really what we are looking at in this decision making, so that the expert has more time to do other things. And one of the reasons I got this fellowship, because the technical director for this industries, he was based in UK, and then these global foundries where one of the founder will always be off the time zone. And then the interest is, if somebody wants to then take his advice, then they will probably go through this AI system, and then your dashboards will have all the information quickly, and then that gets recorded, AI can observe it, and then it will learn from that conversation. That's really the end point we want to go, and therefore we need to build this consortium so that we can approach that challenge collectively.
Sir, I have a question.
Sure.
You mentioned large data set and small data set also.
Yes.
It is like what the outcome of your root cause analysis, how the small data set or large data set will be influencing the outcome.
So typically, there are two data sets now. One is your in-process data for, say, particular batches. So that I call it as a short, small data set, where you have your rejection rates for a particular product for last 3 months. And normally your batches will be 50, 60, 100. So that we call it as a small data set. And if you employ some machine learning techniques, sometimes they need more data sets. So then we augment that data set through our predictive analytics for the machine learning algorithms to work. So that's what I meant by that. But then there is another data set, which we are now looking at, is for training or fine-tuning LLMs, large language models. So then they can, the difference there is we want to, and again, it works on small data sets. But for example, one expert will quantify a particular defect. The person will use a certain language with the same intent. Another person will use different language with the same intent. Humans can understand that. And what we are trying to do now, which working with this Foundry, is to then capture those sentences and then train your LLMs and then integrate that with machine learning algorithms. So it is still small data set. When you look at, say, signal processing, that will then have large data set. That might require, say, thousands of signals where you can then use machine learning algorithms for neural network-based algorithms to train those. So that's my distinction between large data sets and small. So if you want to use image recognition software to identify defects visually, then you don't need only 100 images. You need thousands of images to learn those. So that is a separate problem. And you can use, I think there are now very nice algorithms because of what you call advancement in EVs and image processing for other computer science applications. We can borrow those algorithms, and the commercial companies are doing that to enhance visual inspection. So personally, we are not working on that because we're just letting others to perfect that technology. We want to use that knowledge as one of the pipeline which will feed into our system and then use that in a way expert will use that knowledge for decision making. That's the challenge we are trying to address.
Okay, thank you.
One more advantage for a foundry engineer or the expert is there. He takes the decision and there is nothing to back him.
Yes.
You know, that's very important. If the person working on the shop floor, if he takes any decision and suggests any process change or anything to do or any corrective measures he suggests, that he takes the onus of risk or onus of that decision falls on him. He doesn't have any data. So with this kind of algorithms, he has the perfect, I mean, he has got something to back up with. That is a great advantage. And then this always could be corrected and every correction becomes a case study. So anyway, rest of the things doctor has said already, so I will not get into that.
I mean, that is correctly pointed. The main difference between this philosophy and the traditional ones, that the traditional ones require rule-based systems to capture human expertise, and they don't work because humans don't think it that way. So that's where we also struggled for the last 10, 15 years on capturing human expertise. But this new thing that has happened in the last 1 or 2 years, particularly with generative AI, is a game changer. And that has opened up lots of opportunities to make this happen. And this will sustain. Because if you look at the way FMEA standards and the expectations are changing, if you see the way ISO standards, quality management standards are changing, they all are designed. Effectively, there was a big debate between the existing, how many of you have heard the new VDA AIAG guidelines for FMEAs? Are you aware of the new guidelines? One. Yeah, so very few. Okay. Yeah, but even in academic, we teach FMEAs with RPN number. I mean, they are gone. So the new guidelines are, the way we see it, they are really designed to make computers intelligent rather than help humans make decisions. The old guidelines were designed to help humans to make decisions. But that's really my perception. If you go into details of the new guidelines, they are very cumbersome. They are very challenging. It requires a lot of information. But we are now using ChatGPT to help convert from old guidelines to new guidelines because they are designed to make computers intelligent. And I think that's what Germany is trying to do, with their influence, VDAs, really. That's my personal opinion, to do that. But the whole thing is, as academics, can we prepare ourselves and then use this technology to expand? That's really the kind of collaboration I'm looking for from NIAMT as well.
Actually, sir, to be frank, to my knowledge, I don't think we have included root cause analysis or FMEA or any of these things into our curriculum. Now our department, Foundry Force department, they should think in that particular direction.
I think always we insist for the interdisciplinary studies and interdisciplinary programs. At least may not be the exam paper as such, but at least as a complementary to the students, some kind of lectures with the interdisciplinary activities could be organized, and subsequently they lead to the additional electives for the choice of the students. And then that could be a part of a syllabus. So progressively this could be done. So rather I request NIAMT faculties to come together and design some lectures for the students for their orientation. Thank you.
Even in our curriculum, we have standard courses because there are only a few things that you can teach in 3 or 4 years. But where students learn are year out in industry and their final year project or the MSc project. So that's where then they become very interdisciplinary, and then they can get support from computer science, they can pick up programming skills, but that's where they really sharpen and work with industry. And I think that's kind of role model which I was thinking, when the students are placed in industry for 1 year, and that's where we got very good work done.
So, any more questions from the audience? So, thank you, Professor Ran Singh, for your valuable insights into digital twinning in Foundry Forge for the purpose of root cause analysis. And I hope somebody will take it forward from the particular department. Let us believe. Sir,
Don't say it's somebody. Don't say it's somebody. I will take the initiative and I will see that. I will bring it together. Say it.
yes, sir, I will do it.
Thank you.
Okay. Thank you very much, sir. Thank you very much for your valuable time. Yeah. And I once again apologize for the late starting of the session. Sorry for that.
No worries. I
Thank
thought
you
it
very
was
much,
because of lunch.
Yeah, thank you very much, sir.
Yeah.
Thank you very much.
Yeah. It's a slow process, but we are really interested to connect because we can work with 1 or 2 industries, but to scale up, it needs a lot of time commitment, and we need to train students, etc. And I think that's where you start seeing how academia and industry can work together in a meaningful way.
Sure, sir. Sure. Okay.
Okay. Thank you.
Thank you very much, sir.
Bye.
Yes, sir. Okay.
Yeah, I can hear you.
It was connected.
Can you hear me well?
Yes, sir. We are able to hear you. Okay. Dr. Kedarnath Rane.
Yes.
Okay. Sir, on behalf of NIAMT, I welcome you online. In fact, we would have been happy if you had visited our place in person. And I leave it to you for welcome.
Dr. Kedarnath Rane is a lead research and development engineer at the National Manufacturing Institute, Scotland, with 8+ years of experience in advanced materials and manufacturing process. He specializes in Industry 4.0, metal powders, 3D printing, additive manufacturing, metal forming, and metallurgy. An experienced mechanical engineer, he delivers cost-effective, sustainable solutions, has has published extensively, presented internationally, and is a member of IMEC-E. I request Sir to share his valuable insights.
Okay. Can you see my screen, by the way? Hello?
Yes.
Can
Yes.
you please confirm that you can able to see?
Yeah, we are able to see your screen, sir.
Okay.
Yeah.
So very good morning. So although I am coming from National Manufacturing Institute, Scotland, today I am sitting in Agadir, which is in Morocco. So I am in my Christmas vacation here. And Professor Khandelwal asked me to deliver this talk so that we can share our developments with you, and we can again have some kind of collaborative work together on this exciting topic of digital twinning. My topic of discussion today is on how we can use digital twin technologies to enhance metallic manufacturing, and how this kind of new era allows us to optimize processes and lead us to sustainable development in manufacturing as well as product development. Before I jump to my presentation, I would like to brief you about my organization. National Manufacturing Institute Scotland is a part of high value manufacturing catapult centers. We are located in Scotland, which is a northern part of UK, and we also have some centers in Sheffield and Aberdeen. So we are expanding our centers all across UK. But along with us, we have other catapult center all across UK, which are specializing in various technologies and manufacturing innovations. When it comes to our working model, we sit in middle TRL, where we work on mostly on collaborating academia and industries together to expedite the development cycles of products and processes, where we can use the product which are conceptualized in academia and research institutes to have some verification and some kind of more kind of mature stage of processing as well as product development, so that industries can absorb these technologies and they can use these technologies for again digital and sustainable goals of their developments. Within the NMS, I come from an institute or a kind of center which is called as Digital Factory. A Digital Factory is a part of NMS. Within the NMS umbrella, we have 5 different centers. One of the center, by the way, is called as Advanced Forming Research Center, where we work on forging, forming, rolling, extrusion, multiple forming technologies that may be interesting to you. So I'm happy also to connect with you guys with this kind of peoples around our NMS umbrella. We also have Manufacturing Skill Academy for skill development work. We have lightweight manufacturing. We do a lot of work for aerospace and composites. And we also recently started Digital Process Manufacturing Center, which also allows us to increase the, because, from Scotland perspective, we have many process industries. So we use our digital skills to cater to this kind of businesses. When it comes to Digital Factory, we have 3 different kind of departments, you can say. One is additive and subtractive manufacturing. Other one is digital technologies, and third one is product development and designs. A brief overview about me. I'm coming from, again, not completely forging and foundry technology, but I do have some experience on these topics. I delivered a couple of projects on sheet metal forming and some extrusion related work. So I'm happy to take some questions on in these technologies as well. But moreover, my more expertise is on additive processes, particularly laser-based technologies. I worked on various tools and techniques using Industry 4.0 and then data-driven solutions, basically not on a factory level, but on a process levels. So coming to the contents of my presentation today, I am trying to cover up some of the topics related to smart factory and IoT solutions, which is again very high level of industrial digital twinning and their use. But my expertise lies in monitoring and control of processes. And that's where I delivered a project called as DigiForm, which is how we can make digital metal forming technology for defect detection and defect elimination. And then later stage of my presentation, I will cover process signatures and how we can use these digital tools to identify process signature and make additive manufacturing as a zero defect manufacturing processes. So I think we nowadays see a trend which is called as first part right kind of solutions. So that is where this process signatures and process control comes into picture in additive manufacturing, because we usually deliver mass customization and very complex shapes, and it's very difficult to like monitor and as well as control such kind of processes and such kind of characteristics in the part. So before jumping to my my topic, I just want to give a brief overview of Industry 4.0. Before pandemic level, we all agreed that so lot many industries are coming with their challenges, like try to standardize the process, try to cut down the operating cost, try to minimize the variations within the processes, try to uniform and try to manage the data and how to data carpentry, data warehousing, and all these things. They are the challenges before pandemic. And we also started researching on those topics, which can serve the industry in solving this kind of problem through connectivity, through developing some KPIs and at a high level of industrial automation and control schemes, and then developing the reliable solutions to streamline the process flows and product visibility at each and every stage of manufacturing and each and every stage of evolution of the process. Not only process, but even if you see that in the forging process, I think there are many developments going on in how you can real-time control the microstructure with some parameter, and can we estimate what are the characteristics or the strength of the part during this manufacturing process. So all these things are now available on our systems, thanks to all this connectivity and all these solutions, which are again possible because of the collaborative efforts between different domains. On a very high level, I would like to cover some kind of factory smart systems and IoT solutions, how they are used in various manufacturing researches. For example, IoT solutions allows us to develop a database and predictive maintenance, and manufacturing indices can be found out